Okay, let's explore the function f of x equal natural log x a bit more. We know that this means f of x equals log of x base e. We could write this as y equals log of x base e if we wish. But or we could write this as log x base e equals y. Just changing what we write on the right or left. But what does this mean? According to the definition of logarithms, this means e to the y equals x, right? Remember our definition, log base b of c equal d means b to the d equals c. I'm just using that. Okay. Do you remember from previously the graph of y equal e to the x? That's an exponential growth function. The graph of y equal e to the x looks like this. But if we want to graph f of x equal natural log x, that's the same as x equal e to the y. Here's the graph of y equal e to the x. And the graph of y equal natural log x is the same as not y equal e to the x, but x equal e to the y. The y's and x's are switched, right? X and y are switched. So that means that f of x equal natural log x and f of x equal e to the x, or y equal e to the x, are inverses of each other. Their graphs are just going to have the x's and y's switched. So if you reflect the graph of y equal e to the x about the line y equal x, in other words, if you just switch x's and y's, you get a graph that looks like this. So this is the graph of x equals e to the y, which is the same as y equal natural log x. So if you go to your calculator and graph y equal natural log x, you're going to get a graph that looks like this one. The log graph is often called the turtle of all increasing functions. There's no horizontal asymptote. You can make the natural log graph as high as you please. It's not bounded above, but boy, it's increasing slowly. This is just a very slowly increasing graph, but you can make it as high as you please. There's no horizontal asymptote. There is a vertical asymptote, though. Notice the graph's getting closer and closer to the y-axis. And in fact, depending on what window you use on your calculator, it might even look like this graph touches the y-axis, but it doesn't. It just gets closer and closer. Okay, so let's learn how to find the derivative of natural log x. Say we want to find the slope of the line tangent to this graph of y equal natural log x. Well, there's a reason that this section, 3.6, is after 3.5, the implicit differentiation section. We're going to use implicit differentiation. So we're going to first let y equal natural log x. Okay? In other words, y equals log x base e. I can write that as log x base e equals y. This means e to the y equals x. Now, let's realize that this, e to the y equal x, and y equal natural log x are the same function, the same graph, just written different ways. Okay, so let's find derivative of y with respect to x only using this e to the y equal x notation, because we're more familiar with that rather than this y equal natural log x notation. Let's find derivative of y with respect to x using implicit differentiation. So we take derivatives of both sides. Let's do the easy side first. The derivative with respect to x of x is just 1. Now, the derivative with respect to x of e to the y, I've got an outside function, the exponential function. The derivative of an exponential function is itself. But I've also got an inside function, because remember, y is a function of x. So I have to multiply by the derivative of the inside, derivative of y with respect to x. So I get e to the y, derivative of y with respect to x equal 1. Now remember, the calculus is over now. We want to solve this equation for the symbol, derivative of y with respect to x. But it's multiplied by e to the y. So to undo multiplying by e to the y, I divide by e to the y. But look, what is e to the y? Look back up here. What is e to the y? It's just x. So I've got derivative of y with respect to x is 1 over x. But what's y? Go back up here. What's y? It's natural log x. So here's our big takeaway. The derivative with respect to x, I'm replacing y with natural log of x, is 1 over x. Very important result. This is in section 3.6. It's on page 218. It's something you need to understand where we get it, but also you need to commit it to memory, because we'll use it over and over again.